Logistic functions can be written in the form of f of t equals some limit L over 1 plus ae to the negative kt. A is a constant approximately equal to the number of times that the initial value grows to reach the limit L. K is another constant, which is positive for logistic growth and negative for logistic decay. And then we have the limit L, the upper limit, sometimes called the carrying capacity. Now, logistic functions may also be found in the form of L over 1 plus AB to the negative t, where B is just some base, and it's a constant as well. All right, so when we have logistic growth, we see exponential growth up to a certain point. That point is the inflection point of the curve. It's where the curve switches from concave up to concave down. And at that point, the growth slows, eventually having the population approach a limit or carrying capacity. With logistic decay, it's the opposite. We start off at a high value, reach an inflection point, and then proceed to some lower limit, which the function settles out on. All right, so what type of logistic function is this? Is it growth or decay? If some foxes are introduced to an island habitat where there are few fox predators and lots of resources such as food. At first, the birth rate of the foxes would be quite high, but as time goes on, they would find that the food and space are limited. Would this be an example of logistic growth or logistic decay? Well, since their numbers start off low and approach towards some maximum limit, the carrying capacity, this would be logistic growth. Here we have a function describing the fox's growth, and we want to plot this logistic function using a table of values. So one of the things we can do just right off the bat here from a logistic function is recognize the carrying capacity in the formula. That top numerator, 2000, is the limit L. And so when we're going to sketch our function, we can just start with that. And it is the carrying capacity. It's the most number of individuals that the island can support. Okay. Now, in order to use the table here, we'll want to pick some different times to analyze. So we could start off with just 0. We can do 1, 2, perhaps 4 and 8. And we'll just plug into the formula and get an output value on a calculator. So at time 0, I get 667 individual foxes. That's going to be our initial value. f of 0. Okay. 667. All right, let's try to plug in a 1 now. After 1 year, we've got 1,200 foxes. After 2 years, we've got 1,636. After 4 years, 1952. And after 8 years, we're up to 1999. Okay, great. We just want to connect those points with a smooth curve here. All right, great. What does the limit of the function as t goes to infinity mean in terms of the variables involved in the problem? So we could try to algebraically evaluate that limit just by plugging in the infinity. Sometimes that works. And then we can see what it's headed towards. I'm just going to rearrange it a little. 2,000 over 1 plus 2 over 3 to the infinity, because we're raising it to a negative power. That would be 2,000 over 1 plus basically 0, because when we're dividing a real number by infinity, it's going to head to 0. And so that is going to be a limit of 2,000. What does it mean in the context of the problem? Well, as time goes on, the number of foxes is heading toward 2,000. Okay, now can we find the initial value of the foxes in a slightly different way than we had done above? This time we're going to use a formula for it. So the derivation of the formula goes like this. You plug in a 0 for your variable, and then simplify, and then you reveal a very easy formula for finding the initial value of any logistic function. Let's see how it would work for our problem. We have f of t equals 2,000 over 1 plus 2 times 3 to the negative t. So we want to find f of 0. By plugging in a 0 for t, but that's going to equal 2,000 over 1 plus 2, which is approximately 667. So yeah, we can always use this formula. When we want to know the initial value, just take the limit L and divide by 1 plus A. Assume the function below fits the form of L over 1 plus AB to the negative x. So this time we have an x variable instead of t. Does it show logistic growth or decay? So as the x's increase, the function's value increases as well. So this is an example of logistic growth. We want to find L from the graph, the upper limit of the logistic function. We can see that it's heading toward a limit of 16. So our L is going to be 16. Now we hope to reconstruct the function and find its constants from the graph alone. So can we use that formula for the initial value of a logistic function and plug in what we know in order to solve for the constant A, for example? So they're talking about this point right here, the initial value, which in this case would be f of 0, and it's 8. So let's go ahead and plug that into the formula. 8 equals 16 over 1 plus A. I used that f of 0 was 8 and L was 16. And now we want to solve for A. Okay, we'll get that. We'll get 1 plus A equals 2. Therefore, A must be 1. Okay, we've got almost everything we need now. The only other constant we need for this form of things is the b. So let's pick one point on the graph and see if we can use it to determine what the b must be. Well, this point here looks like a good one to work with. It looks like it hits pretty exactly at 1, 12. So for the combination of x equals 1 and f of x equals 12, we can use that down here to solve. So let's put 12 in for the f of x, 16 for the limit L, A is 1, and we'll plug in an x of 1. Okay, we'll solve that. 12 times 1 plus 1 over b equals 16. 1 plus 1 over b is 4/3. Minus 1 minus 1. 1 over b is 1/3. Therefore, b must be 3. Okay, now can we rewrite the original function using the constants that we had found? So we want 16 on top, 1 plus, our a is 1, and our b is 3. There we go. Okay, we could check it just by plugging in a very large number for x, for example. I'll plug in an x of 100. Okay, it gives me 16, which is good. I can also plug in an x of 0. That gives me 8, which is the correct initial value. And then maybe I'll just check it by plugging in a 1 as well, see if it gives me 12. It does, so it checks. All right, could we use algebra here to find the value of k? That's a little tougher. This one's not written in the same form as the previous question. Here it's in the L over 1 plus AE to the negative KT form. So let's plug in the output value of the function. 257 equals 530 over 1 plus 45 e to the negative k times 7. That's what we need. All right, so we'll get 257, 1 plus 45 e to the negative 7k equals 530. So I'm going to divide here. One plus 45 e to the negative 7k equals 530 over 257. Let's subtract 1 from both sides. Okay, we'll divide. I'll take the ln of both sides. And finally, we'll divide. Okay, I think I'll go ahead and get a approximation to that. I get 0.535.